Welcome to the Nodutalk, the first episode. With this episode, we are taking you back to the basics. Yes, carbon and silicon. The first topic is chemical composition and which how to get the carbide free structure in as-cast condition. Today's speaker, as most of you are knowing, Dr. P.K. Basutkar is a well-known metallurgist, a top-notch metallurgist of India and globally acclaimed metallurgist. He has 55 years plus of experience in metal casting industries. He started his career with General Motors USA, and after coming back to India, he has worked for Tata Motors for most of his career. Along with his career, he has helped many small and medium-sized foundries to better their SGRN production practices. And we are fortunate to have Dr. Basutkar, as he is proudly known, as amongst our today's speaker. Dr. Basutkar, in today's episode, is going to touch upon the following contents: key requirements of chemical composition, carbon and silicon considerations, effect of silicon, effect of manganese, effect of phosphorus, other elements and recommended additions or recommended levels, recommended composition for different thickness of SGRN castings, general guidelines for SGRN composition, and if time permits, quality index. Friends, we are going to complete today's talk in about 45 minutes, and then 15 minutes at the end we will keep for the open house discussion. In between, if you want to ask something, you can send in a chat box. As for the smooth flow of the meeting, we are going to keep you all on a muted muted mode. But you can definitely make use of chat, or you can call me also in between if you want to ask something. We will take your questions and discuss it at the end of the uh, seminar. Now I hand over and invite Dr. Basutkar for his presentation. Dr. Basutkar, please.
Foundryman, and some of you may be knowing me for a long, long time. Namaste. Kastwel is doing a human service in trying to spread the knowledge of SGIN. Did you know that Mr. Subodh Panchal's father started making the SGIN product in 1974 when nobody in India had the courage to dwell into production of ferrosilicon magnesium? He made it. Next generation, Subodh Bhai Panchal took forward, and now the third generation, his children, Amish, um, Hardik, and cousin Jignesh are taking it forward. Fantastic job. And in 1990, Mr. Subodh Panchal came up with a proposal to use the experience of experienced foundermen like Mr. S.D. Gaitonde, Mr. late Mr. S.B. Phatak, and he included me. I was a novice that time, and we conducted programs to educate fresh graduates. And lot of foundries sent their people first time, second time, even third time to attend this course. This course was held once in a year for 7 days, starting in the morning around 7:30 and ending at night 9:30 or 10 o'clock. Subodh Bhai has done a fantastic job, and God bless him, and I hope his tribe increases. Thank you. Now, the key requirements for chemical composition. In gray iron, we are uh, very clear about the properties. The properties of gray iron are basically dependent on the size and the type of graphite. We all seen in gray iron requirements type A graphite, more than 80%, more than 90%, and the mechanical properties and hardness. The flake has to be type A graphite in gray iron. Type B graphite tolerated up to 5 or 10%. Type C graphite means is hyper-eutectic. People don't like it. Type D graphite is undercooled graphite. People don't want it. Type E graphite is still undercooled graphite. People don't want it. So gray iron mechanical properties are dependent on type A graphite and size of the flakes. Normally, people prefer to have flakes of size 4 to 7, and smaller the size, better the properties. In SGN, the properties of SGN are not dependent on the nodules or the graphite shape. Graphite shape is nodular. The mechanical properties of SGN are not dependent on the nodule size or nodule count. It is dependent only on the matrix of the material. There is no effect of carbon and silicon. I'm talking about carbon and silicon because we'll be only talking about five basic properties and one extra parameter. The five chemical composition basic elements being carbon, silicon, manganese, sulfur, phosphorus. And the parameter is carbon and silicon relationship, which we are commonly known as carbon equivalent. So we'll be speaking about the role of carbon equivalent, carbon, silicon, manganese, sulfur, and phosphorus. So there is no effect of carbon and silicon in SgIN because both low hardness, fully ferritic SgIN and high hardness, fully pearlitic SgIN can have the same carbon and the same silicon, and the property will change only upon the matrix. The first low hardness being uh, fully ferritic or ferritic pearlitic, and the other one being fully pearlitic or pearlitic ferritic. So you see, the carbon and silicon do not determine the hardness. The matrix determines the hardness. In addition to this carbon, silicon, phosphorus, manganese, and sulfur, we also have some other alloying elements about which we will be speaking little later. Okay, so let's go to the influencing factors. The most the most important factor in the SGIN is the section size and the cooling rate. This decides the quality of SGIN apart from the microstructure. So when we speak about the carbon and silicon requirements, let's go to the next slide, please. Requirements to achieve a carbide-free structure in the as-cast condition. Okay. We also have to ensure the graphite shape and distribution. People speak about minimum nodularity 85%. I would request all of you to try to aim at as high a nodularity as possible. 95% good. 98% fantastic. 100% difficult, but possible, achievable, that would be superb. So more than 95% should be our aim. And all depends upon the quality of the raw materials, how well we control the process, how well we control the temperatures, how well we control the composition. We are going to speak about these things as we go along. And to obtain the desired microstructure. The desired microstructure being depending upon the requirements of the grade. Next slide, please. The first requirement is in the as cast condition, we should not have any carbide in the casting. In the as cast condition, no carbide in the casting. So the casting has to be carbide free. That is the first requirement. The next requirement is no shrinkage in the casting. So increase the shrinkage we don't have to increase the shrinkage tendency. You just have to make sure there's carbide free structure in the as cast condition. So uh, the casting should not have any shrinkage. The casting should not require any heat treatment to achieve the required matrix. Any carbide in the structure means you have to do the heat treatment. And that heat treatment has to be done at a very high temperature, 930 degrees centigrade, to anneal out the carbides. So we don't want any heat treatment to be done and to remove the carbide. So we must produce the casting carbide free in the as cast condition. What are the solutions for achieving this requirement? The solution is controlling the carbon, controlling the silicon, controlling the carbon equivalent base, which is based on the thickness of the casting and the matrix structure required for the mechanical properties. Next slide, please. This is a very simplified diagram. We'll be going more into this diagram section wise, but look at this thing. to avoid solidification contraction, which means to avoid shrinkage. Now, if you ever want to remember one single good point from this lecture, this point you must remember, make it underline, keep it in your mind, keep it everywhere where you can. The total carbon, this is all final casting. The total carbon of the final casting plus the 1/7 times the total silicon of the final casting should be more than 3.9, equal to least, but it should be more than 3.9. That means final casting, total carbon plus 1/7 of the silicon of the final casting should be 3.9. Look at the line on the left hand side. If your carbon plus 1/7 silicon is equal to, you run some risk. But if it is less than 3.9, see what you get in the casting, excessive shrinkage. So if you have to take away from this today's episode number one important point, please take this equation in your mind. Carbon plus 1/7 silicon should be more than 3.9. Most of the time, the carbon plus 1/7 silicon is around 3.85, 3.8, and sometimes even much less than that thing. And you will see the importance of this line when we go to next 2 or 3 slides. You will see the importance of the line. Carbon silicon, which is in the above ratio, carbon lower silicon promotes chilling. So if you go to lower than 2% silicon, look at the diagram. It shows this tendency to white iron or iron carbide formation. If you go to less than 2% silicon, in normal section sizes, you have a tendency for forming carbides in the structure. So if you have to avoid carbides in the ASCAR structure, you should not be lowering the silicon too much. There are other reasons where you may be required to lower the silicon. That we will see little later. Now let's go on the upper line, upper side line of the window. There is a higher silicon. If you go beyond that silicon, upper line in this case is about 2.75 in this figure. If you go beyond 2.75 silicon, according to this figure, you end up in the area where the casting will have very high impact transition temperature. That means the casting will be having more brittleness. The impact transition temperature will be high. It may be room temperature or even higher than the room temperature. That means above that temperature, the material will be ductile. But below that temperature, the material will be brittle. So you got it now? The most important equation is total carbon plus 1/7 silicon should be more than 3.9. Please keep this thing very important figure in your mind. Silicon should not be lower than 2% for avoiding uh, carbides in the structure. And look at the last line on the right hand side. Total carbon plus 1/3 silicon, 1/3 silicon should be equal to 4.55. Now, this is a very average figure taken for castings with wall thicknesses around 1 to 1 to 3 inches, 25 millimeters to about 75 millimeters. We will be speaking about other ranges also a little bit, but this is the one figure you must keep in mind. So whenever you get a new drawing and whenever you have to determine the composition for the trials, you will first go to the drawing and pick up the minimum and the maximum wall thicknesses in the drawing with the machining allowances. Okay, then you decide what carbon equivalent to do. Let's go back to the slide. Yes, then you will use this. Uh, then you will use this line on the left hand side to determine what is the total carbon plus 1/7 silicon. Is it more than 3.9 or not? When you select the composition, this we will see. How to select the composition, you are coming to. Just a minute. Give me some time. Then your carbon for the carbon equivalent should not be more than 4.55. When you have carbon equivalent more than 4.55, your castings will have graphite flotation, or there could be even exploded graphite. There will be dross, which is a dry slag in the casting. And along with dross and high carbon equivalent and flotation, there could be a possibility of carbon monoxide pinhole defects in the casting. So you see how you have a very, 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 very narrow window to operate with carbon equivalent, carbon and silicon if you want to make defect-free castings. And when we have defect-free castings, we try to run around to find out what is the cause. We will be looking at some of the possible causes which we unknowingly happen to do in the foundry, which causes the problems in the castings, and we do not understand that thing. We will try to recall some of those possible causes if we as we go along. So resistance to carbon flotation may result if carbon equivalent is too high. So carbon equivalent should not be too high, 4.5, 4.55 generally. So keep this figure in mind. Individual section sizes, we will speak about it a little later. Next slide, please. This slide. This is a slide which on the y-axis gives you carbon equivalent values. And on the x-axis, it gives you the wall thickness of the casting, which we also understand is 2 times the section modulus. We have all heard about the word section modulus in the foundry lingo. So on the x-axis is the casting section thickness, and on the y-axis we have got carbon equivalent. Now there are two lines. There's an upper limit to the carbon equivalent. As the section size increases from say half an inch to around 3 inches, the carbon equivalent in the upper limit and lower limit both reduce as the section size increases. Do you notice that thing? Look at the shaded area. This shaded area is bounded by an upper limit for the carbon equivalent. If you go beyond that limit, you run the risk of flotation, carbon flotation, graphite explosion, dross formation, and possibly carbon monoxide pinhole defects in the casting. Look at the lower line, limit line, lower limit. If you go below that lower limit, as the section size increases, the carbon equivalent value decreases. But if you go beyond the lower limit, your castings are prone to carbide formation and shrinkage tendency. And one of the most important reasons for the shrinkage tendency is the cast iron joints. Wherever the sections are joining, then you will always find shrinkage defect. Now that shrinkage defect is because the sand over there gets the heat from two sides of the section. It could be I section, it could be a Z section, it could be a T junction, it could be a L junction, whatever it is. At the joint sections of the casting, you must provide radius. You must provide radius when you are making the pattern. There is no point finding the defect after you make the pattern and then making the radius with a M seal or some kind of a putty. Because you never know during the molding, jolting operation, when that stupid M seal fillet will come out of the pattern, you will never know, and you will find the hard way. You will see some shrinkage in the casting, raw casting after short blasting if you are lucky. If you're not lucky, you will see the shrinkage after machining, where you have added some value to the casting, you have added some machining cost, and then you reject the casting because there's shrinkage at the joints. Or sometimes the shrinkage is found at the customer's end or the supplier's customer's end. And sometimes the customer will find out if there's a failure of the casting. So the shrinkage is mostly foundry responsibility. I'll give you a second small tip. Whatever is the fillet radius mentioned in the drawing, you make your pattern with the fillet radius at least 2 to 2.5 times that radius which is mentioned in the drawing. If the radius mentioned in the drawing is 10 millimeters, you make the fillet radius on the pattern as 25 millimeters. 2 times is 20 millimeters and 25, 2.5 times is 25 millimeters. And you will see, you take any casting in your foundry which you are making today, and you go to the pattern and you check the fillet on the pattern with the help of the radius gauge, and you check the same radius on the casting which is made from that pattern, same cavity, and you will find that the radius on the casting is at least half, if not less than half, excuse me, times the radius on the pattern. Though in SGI and casting, the radius always shrinks. So you make the pattern with the radius made out of the pattern material, and not make the radius on the pattern after you make the casting. That could be a bad thing to do. I hope you understood the reason why the radius is to be applied. Everywhere, every joint, the fillet radius should be there, and it should be starting on the pattern with 2 times whatever is given in the drawing to 2.5 times. Sometimes you may even have to go to 3 times. So when you make the pattern, make sure you measure the radius all over the pattern along with the casting, and then determine if next time you have to increase the to 2.5 times or probably more than 2.5 times. So I hope this point is clear. The fillet radius in the SGN patterns are very, very important because they are the one source of shrinkage because of heat concentration at the joint of the two surfaces. Okay? If you have any questions, write them down. We'll answer the question at the end. Next slide, please. Now, this is a very, very, very important slide. This slide was made by Ductile Iron Society. It's an American Society for Ductile Iron in one of their technical publication called Hot Topics. And this was the role of carbon and silicon in ductile iron. On the um, x-axis, you have the carbon content. On the y-axis, you have got the percent silicon. And this figure has got 4 zones. Right at the top, the blue zone, area 1, indicates the ranges of carbon equivalent, carbon, silicon, and the carbon equivalent to avoid flotation in that blue area. In this whole figure, there's only one line which is a solid black line. Do you see that solid black line at the very left hand side? At the bottom of the figure, this solid black line is carbon equivalent is equal to carbon plus 1 upon 7 silicon is equal to 3.9. It should be 3.9 to or more than 3.9. Okay, so this is the shrinkage. If you want to avoid shrinkage, you must have carbon plus 1 upon 7 silicon more than 3.9. This is the requirement for all the castings of SGI. Then number two, on the right hand side, you have got lines of different uh, shapes. This one, the one for the area 1, highest CMO SG ions. The upper line is carbon equivalent is carbon plus 1/3 silicon equal to 4.85. You see this figure on the right hand side near 3.5 percent silicon. So carbonic, no, the previous slide, please. Yes, the carbon equivalent CMO grades, because these are all thin section castings. They normally used for turbocharger engines, turbocharged housings, turbocharged exhaust manifolds, and many more high silicon and moly containing castings, which are thin wall castings. Now let's go to area 2. Area 2 is thin wall castings. Thin wall casting means having a wall thickness of less than half an inch, which is less than 12 millimeters. Area 2, orange in color. Got it? So in this thin section casting, 12 less than 12 millimeters in thickness, if you want to avoid the shrinkage defect, the carbon equivalent should be less than 4.6. You see on the right at the top of the figure on the left hand side, for this line, the carbon equivalent is equal to carbon plus 1 upon 3 silicon equal to 4.6. For very thin wall casting, your carbon equivalent should not go beyond 4.6. I give you a figure in the previous, I give you a number in the previous slide of 4.55. This is very general figure for most of the casting that we make in our foundries. So thin wall castings, carbon flotation will occur if you go beyond 4.6 carbon equivalent, which is carbon plus 1/3 silicon. The um, left hand side remains the same. Carbon plus 1 upon 7 silicon should be more than 3.9. Now look at the orange figure on the top. The silicon starts with about 2.4% and silicon ends at about 2.7%. So silicon has to be between 2.4 and 2.7. Your carbon equivalent for avoiding flotation is fixed. Carbon equivalent is equal to carbon plus 1/3 silicon should be less than 4.6. Your carbon equivalent figure for avoiding shrinkage, carbon plus 1/7 silicon should be more than 3.9. Got it? This figure is very useful. If you take a photo of these two figures and keep it on your camera or mobile, it will always help you whenever you have to talk about the competition while making the trial of the castings. Now let's go to the purple area, area 3, which covers wall thickness from zero point 0.5 to 1 inch. Zero point 0.5 is about 12.5 millimeters, 1 inch is about 25 millimeters. For this, the left-hand curve is still the same. To avoid shrinkage, carbon plus 1,7 silicon must be more than 3.9. I keep on repeating this thing because I want you to get that into your head. That I must keep the carbon plus 1,7 silicon more than 3.9 in my casting. Now, in this wall thickness of half an inch to 1 inch, if you want to avoid the graphite flotation, your carbon equivalent, again look at the right hand side. For this section size, your carbon equivalent should be less than 4.55. That is, carbon plus one third silicon should be equal to 4.55 to avoid graphite flotation. This was the figure we gave you in the previous two slides. So this is a general figure for all the wall thickness which are normally made in the foundry. But for specific wall thickness, you have to refer to this figure. Uh, I hope this is clear for section sizes from half an inch to 1 inch. Now let's go to the yellow figure at the bottom, the window. The heavier section, this is 1 inch to 3 inches, that is 25 millimeters to 75 millimeters. Again, on the left hand side, it is bounded by the same curve. Carbon plus 1,7 silicon should be equal to or more than 3.9. Again, the carbon for 1,7 silicon should be more than 3.9, again for SGIN. In this case, to avoid this is a heavy section, now to avoid graphite flotation, look at the dotted line on the right hand side. It says carbon plus one third silicon for this dotted line should be 4.45. Got it? So in the CMO grade, it was 4.85 thin wall castings, normally 3, 4, 5 millimeters. Into a less than half an inch, the carbon equivalent for avoiding flotation was 4.6% carbon equivalent. In the medium range, 1 to half inch to 1 inch, the carbon flotation was avoided if the carbon equivalent was less than 4.55. If in 1 to 3 inch sections, the carbon equivalent has to be less than 4.45 to avoid graphite flotation. So you got this, but the left hand side is always carbon plus 1 upon 7 silicon should be more than 3.9. If you have any questions, write it down. We'll come back to this thing because I want you to understand these two functions, the carbon equivalent, carbon and silicon consideration. Now, what does carbon and silicon ratio do in HDIN? After carbon equivalent selection, which we have done, carbon plus 1,7 silicon more than 3.9 and carbon plus one third silicon depending upon the wall thickness of the casting to avoid graphite flotation. This we have done now from the previous thing. Now we have to fix the carbon and silicon. What does the carbon silicon ratio do? You look at the figure to your right hand side. On the x-axis is silicon content. On the y-axis is yield strength. As the silicon content increases, the yield strength in ash cast SGIN, politic or politic ferritic grade increases. So if you have to increase the yield strength, you have to increase the silicon. So the silicon minimum, we said 2%. And maximum, we have seen in CMO, it can go from 4 to 6% silicon. I didn't show you the silicon range in the previous casting. Can we go to the previous slide just to tell the people about the silicon piece? Yes. Look at the silicon in this next one. Yeah, look at the silicon. The silicon is from 3.8% to about 4.2%. Normally in CMO grades, the silicon is um, specified 4 to 6%, along with moly, maybe 0.8 to 1.2% moly. So you see in thin wall castings, silicon can go in CMO grade up to 6%. Now go back to the next slide. Then look at the yield strength in the annealed casting. Again, as the silicon content increases, the yield strength of the annealed HDIN keeps on increasing. And on the right hand side, you have got an elongation curve. As the silicon content increases, the elongation also increases. Okay. Now, after carbon equivalent, we have decided to fix the silicon content. It should be based on silicon's effect. Silicon affects the strength, the ductility, and the graphite refinement. That means the size of the graphite thing. Apart from promoting graphite and refining its distribution, silicon is the most potent beneficial element in increasing strength in the as cast and the as cast ductility. What is the as cast ductility? Will come. Effect of silicon. What are the effects of excessive silicon? If we go beyond the ranges which are given in the diagram of carbon, silicon, carbon equivalent with the section size, if you go to excessive silicon, carbon flotation is possible to occur in thick sections. As you go to excess silicon, you will reduce the impact test energy. This I will show you in the next slide. If you increase the silicon, it will increase the impact transition temperature. This we will see in the next slide. If you increase the silicon, you decrease the thermal conductivity. One of the most important properties of gray iron is thermal conductivity or thermal diffusivity. That means wherever the combustion takes place, the material is able to take away the heat from that area to a cooler place because the graphite particles, flake graphites, are interconnected. In HGIN, the graphite nodules are not connected, and therefore the thermal conductivity decreases as the silicon content increases. But silicon increases the hardness. We'll speak about this increase in hardness when we touch upon the solid solution strengthened SGIN, which have been the latest addition in the family of SGIN. So look at the figure now. The x-axis is silicon content, and the y-axis is the hardness. So in the as-cast condition, the silicon increases the hardness in annealed and the as-cast condition. Any questions? Please write it down. We will answer at the end. Next slide, please. Now, this is the most important slide and most important effect of silicon on the impact properties. Look at the right-hand side figure first, the S-shaped figure. In the middle of this line, there is a point which is known as a transition point, transition temperature. On the y-axis, we have got the impact energy transition temperature, Sharpie impact energy transition temperature. And on the x-axis, we have got the test temperature. On the y-axis, we have got the impact strength. The straight line on the top, it means that the material is ductile. It's got high impact bearing capacity. On the lower side, the lower curves indicate the material is brittle. So the S-shaped curve, the line on the top increases, shows the ductility, and the straight line at the bottom shows the brittleness. So in between is the temperature at which the material changes from ductile material to brittle material. Now, for certain low temperature applications, you require high ductility. So this curve on the right hand side, the first curve is for 1% silicon on the top. The next one is for 2% silicon. The third one to the right is a 3% silicon. So as you increase the silicon content, the transition temperature increases. That means if you have to produce ductile iron casting for standing impact at low temperature, your silicon content must keep on decreasing. And for very heavy section castings, which are used on the ships which are running in the icy waters or in Arctic regions or windmills in very cold conditions, the impact energy is required to be high at minus 20 degrees centigrade and at minus 40 degrees centigrade in the Icelandic conditions. So when you make such castings, your silicon content has to be even probably closer to 1.8%, 1.75%. So the silicon has a very, 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 very large effect on the impact properties. For normal castings, the impact properties are normally not mentioned, not required. But for low temperature or cryogenic applications, you have to keep the silicon on the very low side. Otherwise, even a drop of a hammer, a drop of a screwdriver, a drop of a plier will break the housing if it is kept in the minus 40 degrees or minus 50 degrees. So the effect of silicon on the Sharpie impact temperature, is shown on the left hand side. We just explained. So impact of silicon and other elements on the transition temperature. I told you, if you want low transition temperatures, the silicon has to be low. As the silicon content increases, the transition temperature increases. But apart from silicon, there are other elements which also increase the transition temperature. Nickel, if it is added to 0.1%, will increase the transition temperature by 2.2 degrees Celsius. Manganese, if we add 0.1% extra manganese, it will increase the transition temperature by 5.5 degrees centigrade. Phosphorus, if you add 0.1% phosphorus, your transition temperature will increase by 28 degrees centigrade. Can you imagine? So for these low temperature application, the phosphorus has to be kept less than, mark my words, less than 0.03%, preferably less than 0.015%, because phosphorus is one element you can't take out. You can only control the phosphorus by using good quality pig iron and steel scrap. You don't get very low phosphorus. So for such application, phosphorus has to be as low as possible, most preferably less than 0.015%, but probably 0.2 or maybe 0.21, 0.22. But certainly closer to 0.15 would be preferable. You know where the phosphorus comes from? Steel scrap. There used to be, when I was running for a foundry of making HGN, there used to be something known as a CRCA scrap, which we still all call lot of scrap as CRCA scrap. You remember that? CRCA scrap stands for cold rolled controlled anneal scrap. Cold, R rolled, C controlled, A anneal, CRCA, cold rolled controlled anneal scrap. And the composition of cold roll control anneal scrap CRC was very simple to understand. Remember, less than 0.1% carbon, less than 0.1% silicon, less than 0.1% manganese, less than 0.01% sulfur, less than 0.01% phosphorus. This was the CRCA scrap which was used for more vehicle auto bodies. Now there is no CRCA scrap. There's only HRCA scrap, hot rolled, and the manganese can sometimes be found as high as 1.5% in this scrap. So when you talk about CRCA, that is the history over now. You don't get CRCA. So you understand from this discussion how important it is to keep the phosphorus as low as possible. In normal castings, we should try to keep the phosphorus as low as possible, preferably less than 0.004 or at the most 0.005 for thin wall casting, because phosphorus tends to segregate in the cell boundary. We'll speak about it if time permits, and it causes phosphide formation and shrinkage. That's the reason we have to keep the phosphorus also low. Next slide, please. So carbon loss. Most of the people don't know how much is the carbon loss. The carbon gets lost during the magnesium treatment. When the magnesium treatment is very violent, the carbon loss is more. And when the magnesium treatment is very a small quantity, the carbon loss is more. And the silicon, uh, if it is low, it is difficult to achieve yield strength. We spoke about that thing. And if in low silicon composition, if you have to maintain the silicon low, you would have to add some nickel to improve the yield strength. Next slide, please. I'm rushing through because I don't have too much of time just now. This is the effect of manganese. Gentlemen, in India, most people use manganese as alloying element. Manganese in HGN should not be more than 0.3%. You look at this curve on the right hand side. As your wall thickness increases beyond 1.5, 1.6%, the manganese should be closer to 0.2%. Anything more than 0.2% is dangerous for the casting. You know why? Because whatever the manganese is present in your liquid iron, let us say it is X% present. When that liquid iron solidifies into castings of heavy section, there is segregation of manganese, which manganese, which is in liquid ion of X%, segregates to 10 times this value. That means in the casting, heavy section casting, the manganese will be as much as 10x. So if your casting liquid metal has got zero point 0.5 manganese, the heavy section casting will be having up to 5% manganese. And this manganese in the heavy section is, it creates such a stubborn carbide that if you are doing any drilling operation, first it will wear out the drill. The drill will not move any further. In worst case, it will break the drill. People don't realize that thing. Your machine shop wala will come howling at you. So please don't use manganese as an alloying element. Keep the manganese as low as possible. I'll give you one table in another 1 or 2 minutes to tell you how much should be the manganese in various section castings. Purpose is it is independent of the desired matrix and it prevents carbides in the as cast condition. Next slide, please. This is what happens when manganese segregates. When manganese segregates in the heavy section, it forms this white area which is carbides, very, very stubborn carbides. They break the tool of your castings, of your drill tips. Next slide, please. So this is the effect of phosphorus on the fracture resistance. Phosphorus in ductile iron should be 0.03 maximum, 0.04 and up to 0.05 depending upon the silicon content. In mixed ductile and brittle, it can go up to 0.06, 0.07. You will have mixed structure. And very brittle ductile iron if the cellular phosphorus goes beyond 0.1%. Next, please. This is the effect of phosphorus segregation. It gives you shrinkage as well as white areas are phosphide eutectic. Phosphide. Next, please. There are other elements which also cause harm to your casting. Carbide promoters and stabilizers. Chromium should be less than 0.05. Vanadium should be less than 0.03. Boron. Boron plays havoc with your politic ductile iron. It causes drop in the hardness of the casting. Tellurium less than 0.003. Where does tellurium come from? Sometimes we use this tellurium coated CE cups in the foundry. And after the cup is over, you take that very cup and put it in a furnace. That's where the tellurium in the metal comes from. All the CE cups should be buried in the ground outside the foundry. No other bit of this cup should go into the metal in the furnace. Molybdenum 0.01 to 0.75 depending upon what grade of casting you are making. Now look at this list of tables which tells you the limit or the elements. Do you have any of these elements in your spectrometer? How will you ever come to know what is the level of these elements in your castings? Do you have the channels for these elements in your spectrometers? And are those channels calibrated with standard material to know what the element concentration casting is? Please consider this table as a very useful table to decide when you're selecting a spectrometer and the channels for the spectrometer. Next slide, please. Yeah, this is a very important figure. This is another slide you must take a photograph of and keep it in your mobile. Now there are three tables on the left hand side and three tables on the right hand side. These tables cover castings of wall thickness of 12 millimeters, up to 25 millimeters, up to 50 millimeters, up to 100 millimeters, to 150 millimeters. So you see this castings probably cover about 85 to 90% of the castings made in the foundries all over the world. Now the first table on the left hand side on the top, it tells you the maximum values that can be tolerated in these castings of this wall thicknesses. These wall thicknesses are common for all these 6 tables, okay? Now sulfur maximum. The maximum sulfur in the final casting should not be more than 0.012. And on the lower side, around 0.008. In some methods of making HGN, like the Fischer converter process or the pure magnesium process, the sulfur will probably go to 0.003, 0.004, 0.005. This affects the nodularity of the graphite. In such cases, we sometimes have to add sulfur to the metal after treatment. Phosphorus maximum, once again, I am repeating what I told you earlier. Any wall thickness, phosphorus should not be more than 0.03%. Chromium, we sometimes mix the grades of gray iron and SG in case we are making gray iron in a foundry. Chromium should not exceed 0.05%. Cerium, this comes from our ferrosilicon magnesium because of this, some of the bad elements I just showed you a little while ago. To neutralize their effects, we have cerium. So cerium limit for all these wall thicknesses is around 0.025. People have cerium channel in the spectrometer, but how often is this cerium channel calibrated? Excess of cerium will cause chunky graphite in a microstructure. Nickel, sometimes earlier people used to use nickel magnesium alloy. So nickel up to 0.1%, up to 25 millimeters, and can go up to 0.4%. Now the next two tables on the left hand side are for ferritic ions. 400 by 18, 400 by 12, 450 by 15 is in the second table, and 500 by 7, 500 by 7 GGG50 is at the bottom table. Carbons, silicon, manganese, copper, for all these, the rest of the tables now. The other elements we just covered in the top table. Now, carbon, as the wall thickness increases, the carbon content decreases. As the wall thickness increases, the silicon content decreases. Why? We have seen in those figures. As the wall thickness increases, we have to reduce the carbon equivalent to avoid the graphite flotation in the casting. Now, manganese maximum in these ferritic grades. See the figure 0.2%. Please go back to your foundry and check how much is your manganese. Copper maximum 0.1% for all the wall thicknesses up to 6 inches, 150 millimeters. Go to 500 by 7 grade. As the section size increases, the carbon reduces. Same reason. As the section size increases, the silicon reduces. Same reason, to avoid graphite flotation. Manganese maximum 0.2%. As the section size increases, maybe up to 0.25%. Copper max 0.25% to get little pearlite in the 500 by 7 grade. Look at the right hand side figures. This is pearlitic ferritic grade, GGG60. Carbon, as the section size increases, carbon content decreases. Silicon decreases as the section size increases for the same reason, to avoid graphite flotation. Manganese 0.25 in the thin section and 0.3 max up to 6 inches. Copper max depending upon the section size to get the pearlite content in the matrix. 700 by 3. As the section size increases, carbon decreases. As the section size increases, the silicon decreases. Why? To avoid graphite flotation. And manganese 0.25 in the thin section and 0.3 max in the heavier section. Copper max to get the required pearlite in the structure. 800 by 2 can be obtained in the as cast condition. Same thing about carbon. As the section size increases, the carbon reduces, the silicon reduces to keep the carbon equivalent low to avoid graphite flotation. Manganese, again, maximum 0.3. Copper, depending upon the amount of pearlite you want. Nickel, to get the fineness of the pearlite. So this is a very important figure when you are planning trial production for keeping a composition. Carbon equivalent, carbon and silicon, these have to be within a very, 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 very narrow window to get good quality castings. Next slide, please. This is a very useful slide. It was provided by late Mr. Ramurthy in the SGI and casting technology book, which is available with Kastwel, and Kastwel has done a fantastic job. It gives you the minimum wall thickness of the casting, gives the maximum wall thickness of the casting, and for the matrix of predominantly pearlite and predominantly ferrite, how much should be the total carbon, total silicon, and carbon equivalent to avoid the defects which we spoke about. Next slide, please. So guidelines for making SGI. Carbon and silicon values are almost the same for ferritic and pearlitic grades. We have seen that thing. The carbon equivalent depends on the section thickness of the casting and not much on the matrix of the casting. Manganese content can be higher for pearlitic grades, but it is advisable to limit the manganese content to 0.3% for all the grades. For manganese levels of 0.3, The required addition of copper will be as given over here, depending upon the grade. The target compositions are of final castings. This will include silicon recovery from magnesium alloy and inoculant and also carbon loss. Last slide, please. Next slide. The key factors, raw materials, process parameters. We will be speaking about these topics in our subsequent talks. Critical characteristics of high quality SGIN, high nodularity, aim for more than 95%. And please don't let the stupid image analyzer of your microscope tell you the nodularity. You see with your own eyes and compare the nodularity with the standard table charts given by AFS or by SNAM or anybody else for nodularity reading. High nodule count. For impact properties, we don't require very high nodule count, about 250, 260 is fine. But I would like to tell you, get as high a nodule count in a regular castings as you can possibly get by good inoculation, which we will be speaking in one of our lectures, absence of carbide, low phosphorus content, less than 0.03, and freedom from any intercellular porosity. And the next slide I will cover in the next time because
Section thickness or upper or lower thickness?
I'm sorry, I'm having some difficulty in listening to you.
Can you hear me now?
I can hear you now.
Yeah. The section thickness, which was mentioned in the table, means upper section thickness, lower section thickness, or average section thickness.
That answer you will get in the slide which says minimum wall thickness and maximum wall thickness of the same casting. That answer you will get over there. You must know the minimum wall thickness. Don't take ribs into account. Normally, ribs are for reinforcement. They're about 4 to 5 millimeters thick. The reinforcement ribs, you can forget it. But look at the minimum wall thickness and the maximum wall thickness in the same casting. If you are not able to do that, then take a nominal wall thickness. What is most of the casting of wall thickness kitna hai? That's the nominal wall thickness. But
Yeah.
pay more attention to the fillets.
Okay. Okay. The second question is, to avoid the shrinkage in high CMO grade, what
Yes.
chemistry should be maintained?
What?
Chemistry.
Chemistry, depending upon the wall thickness, your carbon will be around 3.3 or 3.35 because your silicon is on the higher side. In CMO grade, your silicon may be 3.8 to 4.2. So probably keep the silicon around 4%, for example. Let us take 3.9, for example. So 3.9 divided by 3 is 1.3. And your carbon equivalent has to be less than 4.85. So 4.85 minus 1.3 is 3.55. So your carbon can go up to 3.55.
We are looking for a ductile iron which is having minimum 300 BHN hardness with a ductility of say 5 to 7%. But due to the some application constraint, we are not supposed to do the heat treatment. So, Basudhar sir, can you suggest some chemistry or something how to achieve
Yeah,
this property?
just tell me the wall thickness of the casting.
Wall thickness we have a minimum 8 mm thickness and as high as 15 mm.
Okay, so 8 to 15 mm. Okay, approximately half an inch.
Yes.
3 millimeters this side, 3 millimeters that side. It's about half an inch. So refer to the table and you want to make it in as cast condition without heat treatment.